Hello, I Rajesh Kumar again here. Today we are going to discuss about the optical isomerism. Now, what is an optical isomerism? It is a property of molecule in which all the physical and chemical property of the molecules are the same, but they differ in respect of the rotation of a plane of a polarized light. Such molecules are said to be the optical isomers, and this phenomenon is said to be the optical isomerism. The optical isomerism of a molecule is always measured in terms of the specific rotation. A specific rotation can be defined by the rotation caused by the solution of 10 centimeter in length and unit concentration of the light of a given wavelength at a given temperature is called the specific rotation. So, a specific rotation alpha is equal to rotation observed upon L into C of a given wavelength and temperature T degree centigrade. So, rotation caused by the 10 centimeter in length of solution or at a given temperature and wavelength of unit concentration is called a specific rotation. Now, light. A new term was explained here, plane of a polarized light. What is a polarized light? Polarized light, normally light always travel in a straight line, and during this very traveling they always vibrate right angle in the direction in which the light travel. The vibration is always takes at a right angle in the direction in which light is going to travel here. But in case of polarized light, when the light travel in a straight line, there are along that very line there are infinite number of planes. A normal light always propagate in all the direction along that very plane. That is called a normal light. But polarized light always propagate in only one direction. This is the difference between a normal light and a polarized light. Normal light, like this one, it is going to travel in direction. It going to propagate in all the direction here, 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 here. So this is the propagation of a normal light. But in case of polarized light, it propagate in only in one direction. This is called polarized light. So this is your normal light. This is your polarized light. A normal light can be converted into polarized light when it passes through a specific prism known as Nicol prism. Nicol prism is nothing but it is made up of calcium carbonate crystals that is called calcite. The specific rotation is always detected and measured by a specific device that is called polarimeter. Polarimeter is a device which is used to detect and measure the specific rotation of a polarized light by a solution of 1 centimeter in length and unit concentration, that is 1 gram per liter concentration of the solution of the optically active substance. Now, what is polarimeter? It is a long tube-like structure, consists of two ends. At both ends there are lenses, and it will cause the rotation from here. Light enters through this one and emits from another side. This part is called analyzer and this part is named as polarites. Analyzer always analyzes the rotation. If there is no rotation is caused, 100% light or complete light strike your eye, and there is no, whatever light has been entered, emitted light will get equal amount of the emitted light is present there. But if substance is optically active, means it causes the rotation of plane of polarized light, if whatever light has been entered inside this fairy tube, the emitted light is not as good as the entered one. The amount of emitted light is less than the entered light one. So, by adjusting this very analyzer, we can measure this rotation. This rotation may be caused either left or the right as the one faces the sources. So, on this basis, this rotation is of two types. One is called D form, another is called L form. Later on we will discuss what is D form and what is the L form. First, we will discuss something about the historical background of this very optical isomerism. The foundation of isomerism was led by the two gentlemen. One was called J.B. Biot, another is Louis Pasteur. They were observing the crystals of sodium ammonium tartrate, and they observed that the crystals, both crystals are quite different. Both were, one is left-handed, another was right-handed, and the solution of that mixture, left-handed and right-handed, was optically inactive. But when they separated both, it was observed that the solution becomes optically active. Here it is very important to write down here today. This is not the property of crystal, rather it is the property of molecule. It becomes optically active. Now, on this basis, the optical activity is of the following. On the basis of optical activity, the molecules can be categorized in the following four types. One, D form, another L form, another racemic mixture, and another one was mesoform. One by one, we will discuss what is D form, what is L form, what is racemic mixture, and what is mesoform. Till now, we have studied those organic molecules which are capable to rotate the plane of a polarized light, means those light which vibrate in only one plane after passing through the Nicol prism, are called optically active molecules. And those molecules which cannot rotate the plane of polarized light are called optically inactive molecules. On the basis of optical activity, the organic molecules are further categorized into following four types. One is called D form. Or dextrorotatory. Another is called L form or levorotatory. Another is said to be racemic mixture. And another one is here. Another one is here, mesoform. So, there are four types of organic molecules are available here. That is, one is called dextrorotatory, another is called levorotatory, another is called racemic mixture, another is called mesoform. Upper two one is optically active, but lower two one is optically inactive. How? We will discuss each one by one. Now, D form or dextrorotatory. These are the organic molecules which are capable to rotate the plane of a polarized light towards right as one faces the sources, are called dextrorotatory. And L form, those organic molecules which are capable to rotate the plane of a polarized light towards left as one faces the sources is called levorotatory. Equimolar mixture of both means D form and L form have the equal power of optical rotation but in opposite direction are called rasic mixture. These molecules are optically inactive due to external compensation. Means both D form and L form ultimately cancel out the rotation completely there. That's why such molecules are optically inactive. Another form is mesoform. These molecules are also optically inactive, though the factors responsible for to cause the optical activity are available within the molecule, but due to certain reason, that reason the presence of the element of symmetry are optically inactive. Now question arises, what is the main cause of optical activity? Why a molecule is said to be the optically active? Why a molecule is capable to rotate the plane of polarized light? Why one is not there? Now come on, we will discuss each one. First, what is the main cause of optical activity? In textbook it has been mentioned that it is a chiral. Chiral means dissymmetric. Literally it was being said that molecule having non-superimposable mirror image and having asymmetric carbon atom are called chiral. Actually the chiral is a word which means dissymmetric. The L molecule having no element of symmetry are optically active. Or those molecules which have the non-superimposable mirror image are said to be the having dissymmetric molecule having non-superimposable mirror image are optically active are said to be the chiral. As for example, come on here. This is the carbon here. Its non-superimposable mirror image is like this one here. So both are dissymmetric, having no element of symmetry, and both are the non-superimposable mirror image to each other. These are such molecules are said to be chiral. Actually, the main reason of the optical activity, the presence of dissymmetric, means there is no element of symmetry is present. Now, what is the element of symmetry? There are following 4 types of element of symmetry. First, plane of symmetry. Second is called center of symmetry. And third one is called alternating axis of symmetry. Alternating axis of symmetry. These are said to be the plane of symmetry, element of symmetry, plane of symmetry. When the molecule can be divided into 2 equal halves through any plane is called plane of symmetry. Take one example, it is a tartaric acid. This molecule can be divided into 2 equal halves from the mid. This is called plane of symmetry. So the plane through which a molecule can be divided into 2 equal halves, it is called the plane of symmetry. If the molecule, second point, that is your center of symmetry. If the molecule has a center of symmetry, means if it is a cyclic molecule and from the mid of this center of this molecule a line is drawn towards one group and equally extended to the another group and both are at equidistance, this type of center is called a center of symmetry. Now we are going to discuss about the center of symmetry in next. Now we are going to discuss about the center of symmetry. It can be defined as a point in a cyclic molecule. Take one example here. This is ketopiperazine. It is a biomolecule. In this molecule, consider a point, and from this dry line towards an extend backward. So it's going to join two like groups together. Similarly, it is going to join two like group. Similarly, it's going to join two like groups. Similarly, it is going to two like groups. It is also going to join two like groups. Ultimately, a center has been emerged. This center is called center of symmetry. If such molecules which have a center of symmetry are said to be the symmetrical molecules, and these are optically inactive. Another one, take another example. This is your transpiperazine. This is your transpiperazine, and this is your cispiperazine. Cispiperazine is optically inactive because due to one reason, there is no center of symmetry. These two groups are not going to align together, or in line joining both groups, not passing through a particular center there. That's why there is no center of symmetry. But in this case, in transform, there is a center of symmetry, because when the line aligning two different groups opposite to each other, they are passing through the center of this phase cyclic structure. That's why it is called center of symmetry is present there. Such molecules are optically inactive, but dietary molecule cis form is optically active due to the non-presence of center of symmetry. Alternating axis of symmetry. In IIT JEE syllabus, we don't have to study more about this alternating axis of symmetry, but briefly we are going to discuss something about the alternating axis of symmetry. When a molecule is rotated along the axis passing through it, after Q rotation, the rotation is indistinguishable from the previous one, and it is perpendicular to the mirror image. Such is called alternating axis of symmetry. In other words, we can say briefly that when a molecule is rotated and after Q rotation, it is indistinguishable from the initial one. This is called alternating axis of symmetry. Now, if the molecule has any type of symmetry present, the molecule is said to be optically inactive. Means we can say a molecule is only optically active when it has no element of symmetry, means molecule is dissymmetric. So dissymmetric or dissymmetry is the most important factor to make the molecule optically active. Now we will discuss one after another about the D form, L form and everyone. So we were discussing about the element of symmetry. Last time we have categorized and classified the organic molecules on the basis of their optical activity. Last type are the mesoform type or mesotype. Mesotypes where molecules are optically inactive due to internal compensation, because such molecules have the element of symmetry, means these molecules are symmetrical. Due to the presence of symmetry, molecule is said to be optically inactive. So most important factor that makes the molecule optically active, it is the presence of dissymmetry, that is called chirality. Okay, so now we will going to discuss manner by which the molecule become optically active. So there are two words we have studied. One is symmetry, second is dissymmetry, and last one is asymmetry. Now, what is asymmetry? It is very common. A student used to say that there is no asymmetric carbon or there is asymmetric carbon that is optically active or inactive. On that basis, the presence of asymmetric carbon atom, the molecule could be decided whether it is optically active or not active. But this is not 100% true. Now, what is asymmetric molecule? Those dissymmetric molecules which have asymmetric carbon atom, means those dissymmetric molecules which have asymmetric carbon atom, means those carbon atoms with which 4 different groups are present are called asymmetric carbon atom, are present, are called optically active molecules. So it is not important the molecule has asymmetric carbon atom or not, whether the molecule is dissymmetric or not. It is important here. In so many molecules are available where there is no asymmetric carbon is present, however, the molecule is optically active. So this is a skill to decide whether the molecule has asymmetric carbon atom or not, to make the molecule optically active or inactive. This is wrong here. So here the dissymmetric is the important factor, and those dissymmetric molecules which have asymmetric carbon atom are called optically active molecules, are optically active. Actually, the presence of dissymmetric carbon atom makes the molecule dissymmetric. Presence of asymmetric carbon atom makes the molecule dissymmetric, and that's why the molecule becomes optically active. It is very important. Such type of carbon atom is also called chiral carbon, and such carbon atoms can mix the non-superimposable mirror image. So non-superimposable mirror image both are optically active due to the presence of asymmetric carbon atom, means molecule is dissymmetric, are called enantiomers. So enantiomers are the isomeric pair which are mirror image to each other, and they both are optically active, but together in equimolar concentration with equal power of rotation, they are optically inactive due to the formation of racemic mixture, and this racemic mixture is optically inactive due to external compensation. So it is very important to make it asymmetric carbon atom. Asymmetric carbon atoms are those carbon atoms which have 4 different groups. It is always sp3 hybridized. sp2 or sp hybridized carbon atom never happens to be a asymmetric carbon atom. It is also important to know malic acid and malic acid. Malic acid is a geometrical isomer having double bond within the molecule, while malic acid is an optical isomer having hydroxyl group at carbon number 2. So one is the optically active, another is a geometrical isomer. A geometrical isomer exhibit geometrical isomerism. Now in next part we will study about those molecules which are optically active but they have no asymmetric carbon atoms, and we will also in next part discuss something about the total number of optical isomers formed by a optically active molecules. Thank you. Now we are going to calculate the total number of optical isomers formed by optically active molecules. For this, the molecule can be categorized into 2 types. One is those molecules in which are cannot be divided into 2 equal parts. means the molecule is asymmetric. So in such molecules, total number of optical isomers is equal to 2 raised to the power of n is equal to a, where n is equal to total number of asymmetric carbon atom, where n is the total number of asymmetric carbon atom. As for example, so these two carbons are, this molecule cannot be divided into two equal halves. So in this molecule, the asymmetric carbon atom, total number of asymmetric carbon atom is 2 here. So total number of optical isomers is equal to 2 raised to the power of 2, that is 4. Okay. Total number of enantiomers pair is equal to E by 2. Total number of racemic mixture is equal to A by 2, and total number of mesoform is equal to 0. Therefore, ultimately we can say total number of is equal to m of configurational isomers is equal to A plus n. So in this case, the total number of optical isomers are 2 raised to the power n, where n is the total number of asymmetric carbon atom, and total number of mesoform is m, that is also a type of configurational isomer, though the molecule is optically inactive. So ultimately, total number of configurational isomers is equal to A plus m. Optical isomers plus mesoform, both are total A plus m will give us. But if the molecule can be divided into two equal halves or two equal parts, then the total number of optical isomers can be calculated by the other formula. Come on, we will discuss each one by one here. Second one is those molecules which can be divided into two equal parts. So total number of geometrical isomers depends upon the total number of asymmetric carbon atoms present with the molecule. When the molecule has the even number of asymmetric carbon atoms, so in first condition, molecule has even number of asymmetric carbon atom. Then total number of optical isomers is equal to 2 raised to the power n minus 1 is equal to a, where n is the total number of asymmetric carbon atoms. Total of number of instantaneous period is as usual, that is a by 2. Total number of reaction mixture is equal to a by 2 as usual, but total number of mesoform is equal to 2 raised to the power n by 2 minus 1. n by 2 minus 1. n by 2 minus 1 and is equal to m, and total number of configuration isomers is equal to E plus m. So in this very case, the total number of optical isomers has been changed and total number of mesoform also been changed here. Again, another condition, when the molecule has odd number of asymmetric carbon atom and the molecule can be divided into 2 equal half to equal part. So when the molecule type B has odd number of asymmetric carbon atom then the total number of geometrical isomers is equal to 2 raised to the power n minus 1 minus 2 raised to the power n minus 1 by 2 is equal to a, and again the total number of mesoform has been changed, that is equivalent to 2 raised to the power n minus 1 by 2 is equal to m. So total number of geometrical isomers and total number of optical isomers has been changed. If the number is odd, a total number of optical isomers has also be again changed when the number is even here. So in this way, we can count the total number of configurational isomers as well as the total number of optical isomers as well as total number of mesoform here by this method. So we have studied till now about the optical activity and optical isomers. Now we are going to discuss about the enantiomers. What are the enantiomers? Those configurational isomers which are the mirror image of each other are called enantiomers. Now we will discuss about the properties of the enantiomers or enantiomeric pair. The enantiomers have same physical as well as chemical properties. They have everything same except their optical activity. Enantiomeric pairs differs in respect of optical activity. One enantiomer may happen to be deformed or dextrorotatory, other could be of or will be levorotatory. So they differ in respect of the rotation of the plane of polarized. These are called enantiomers, remaining other physical and chemical properties remain same here. Those optically active molecules which have no mirror image are called diastereomers. They are optically active but they have no mirror image are called diastereomers. Diastereomers have different physical as well as chemical as well as optical properties. They have different solubility, they have different melting point and boiling point, they have different crystalline shape. So they differ in all respect, physical as well as chemical property. They have different reactivity towards the chiral and achiral molecules. Since the diastereomers have different solubility in the solvent, so they can be isolated and separated by the fractional distillation. Since they have the different shape of their molecule and geometry of their molecule, so they can also be isolated by the crystallization and chromatographic process. So these were the properties of diatomers and enantiomers. In the next part, we will discuss about the optical activity of those molecules which have no asymmetric carbon atom, but whole molecule is dissymmetric, and hence the whole molecule is optically active. Thank you very much. Till now we have studied about the isomerism, or basically the optical isomerism. It has come to know our knowledge that a large number of compounds are known. Those were optically active due to the presence of the asymmetric carbon atom or carbon atom. But a large number of compounds are also known which have no asymmetric carbon atom. Nevertheless, the molecule is optically active. As for example, alkenes, alkylides, the spiro compounds, well substituted biphenyls. These are the compounds which have no asymmetric carbon atom. However, the molecule is optically active because whole molecule itself is symmetric. Whole molecule itself asymmetric in nature, though they don't have any asymmetric carbon atom. In case of alkenes, take here the example. This is alkene having cumulative double bond in the molecule. This alkene is optically active. Always remember, this is optically active. But those alkenes which have odd number of double bond present in the molecule are optically inactive because the both terminal end makes the molecule symmetric in nature. So those alkenes which have even number of double bond are optically active, and those which have odd number of double bonds are optically inactive because whole molecule itself dissymmetric in nature. In case of alkene, this whole molecule is not like this manner, like this manner. In this way, the whole molecule becomes dissymmetric in nature. That's why it is also optically active. Similarly, in the case of alkylides. In case of alkylides, this is alkylidine. Its molecule itself is dissymmetric in nature. That's why molecule itself optically active. Or in case of a spiro compound, in a spiro compound, one carbon is common with both ring, and such compounds are optically active because whole molecule is dissymmetric in nature. Such compounds are a spiro compound where one carbon is common in both ring, and that's why it is dissymmetric in nature and whole molecule optically active. And well substituted biphenyls. Take here another example. This well-substituted biphenyl is optically active due to the rotation of single bond around this biphenyl there. So due to this rotation, the molecule itself optically active, and optical isomers thus produced due to the rotation of the single bond is called atropoisomers. And this phenomenon is known as atropoisomerism. So it is not necessary that molecules should have a asymmetric carbon atom present. Rather, it is important that whether the molecule is dissymmetric in nature or not. This last step explains that the dissymmetric nature of the molecule makes the molecule optically active. So the presence of asymmetric carbon atom makes the molecule dissymmetric. So dissymmetry is the important factor making the molecule optically active. This is all about the optical isomerism. Next part, we will study something more about this one. Thank you very much. Today we are going to discuss about the another type of stereoisomerism, that is called geometrical isomerism. Geometrical isomerism is exhibited by those molecules which are unsaturated having double bond or alicyclic ring in their molecule. In this type of isomerisms, isomers differs in respect of attachment of the group or atom above and below the plane of the molecule. It is of two types. One is called cis type, another is called trans type. In case of cis type, both groups are attached a side or like side of the plane. But in case of trans form, both group or groups around a double bond lies above and below the plane, so makes the molecule trans form. Now, stability. Trans form seems to be more stable than cis form because it makes the molecule symmetrical in nature. So trans form is more stable than cis form. There are some characteristic features of geometrical isomerism. We will discuss one after another point wise here. In making of geometrical isomerism, terminal alkenes never exhibit geometrical isomerism. Like see here, CS2 double bond CH, CS3, CS2, CS3. So this type of alkene never exhibit geometrical isomerism. Next point, if like groups are present either on one carbon or both carbon, in case of internal alkene, they also do not exhibit the geometrical isomerism. As for example here, this type of internal alkene never exhibit geometrical isomerism. Okay. Cis form may have high boiling point due to its high refractive index, high density, high polarity. This is called our Skita rule. Trans form has high melting point because the molecule is symmetrical, and due to symmetrical nature, packing is perfect, and that's why it has high melting point. This is something about the cis and trans form of geometrical isomerism. Now come on the E and Z nomenclature. Cis and trans nomenclature is possible when on both carbon around a double bond, two different groups are present there. But on both carbon, four different groups are present, then E and Z nomenclature is valid, not cis and trans nomenclature is valid. This nomenclature is based on CIP rule on the priority basis. In case of E and Z nomenclature, first we will decide which has the more priority or more preferential group present on each of the carbon. Okay, so on this carbon, suppose this is more preferential group, and on this carbon more preferential group is this one, then both preferential groups are present opposite to each other. This is called E form. E for integer. Integer means opposite. If both preferential groups are present like side, this is called Z form. Z stands for disseminate. Disseminate means same side. Now we will discuss about how to decide which one has the more preferential group on each carbon atom. For this, CIP, Kong, Ingold and Porlog has suggested some rule concept. This is called CIP rule, or CIP rule follows the following concept and following points as follows. Next part we will discuss about that one. Thank you. The group of higher priority is decided by the atomic number of the atom or the group. The group of higher atomic number has given the first priority. If next point is, if the groups are isotopes, then the isotope of higher atomic number is given the first preference or higher preference in deciding the preferential group there. So two factor, one is atomic number. Any atom of higher atomic number is given the first priority. If they are isotopes, isotopes of higher atomic number is given the first priority. If it is group, in case of group, the group of first atom of the group will decide the priority of the group. First, if the atomic number of first group is higher, that will given the first preference or higher preference in order to decide the preferential group or preferential order in the group, among the groups. If the preference is not going to be decided by the first atom of the group, then we will consider the second atom, and consequent atom could be considered to decide whether the group is first of higher priority or lower priority. In case of double bond and triple bond, all double bond and triple bond is considered equivalent to that very number of 2 or 3 number of single bond. So in this way we will decide which group is given first priority or which group is given second priority here. After deciding the priority of the group, we will decide whether the molecule is of E form or whether the molecule is of Z form. So in deciding the priority of the group, first we have to decide the atomic number of the group. If the atomic numbers are the same, that is they are isotopes, then the isotope of higher atomic number is given the first priority. If it is the group, the first atom of the group which is bonded to double bonded carbon atom will decide the priority of the group on the basis of the atomic number. If the preference is not going to be decided by the first atom, then we will consider the second atom, and consequent atom could be considered to decide whether the group is of higher priority or group is of the lower priority. And afterwards, if it is a double bond or triple bond, it is considered equivalent to 2 or 3 single bond. That's what. Hello, hi, Rajesh Kumar from AIC, again discussing the part of the geometrical isomerism. Today we are going to conclude about this chapter, and last part is here to calculation of the total number of geometrical isomers formed by a molecule. To calculate this total number of geometrical isomers of a molecule, we can categorize in this very part into two parts. One, in those molecules when the both end of the molecule is unlike. In such a cases, total number of geometrical isomers is equal to 2 raised to the power of n, where n is the total number of double bonds. And second category is here when both ends of molecule is like, then this type of molecule, to calculate total number of geometrical isomers for such type of molecule, we can categorize into two types. First, A type, when the molecule has even number of double bonds. When the molecule has even number of double bonds, then total number of geometrical isomers is equal to 2 raised to the power n minus 1 plus 2 raised to the power n minus 1 by 2. N by 2. And B, when the molecule has odd number of double bonds, then total number of geometrical isomers is equal to 2 raised to the power n minus 1 plus 2 raised to the power n plus 1 by 2 minus 1. So this is the total number of geometrical isomers formed by the molecule here. Thus, this is all about the isomerism chapter for IIT JEE Entrance Examination. This type of question could be only asked here. Go through the question. Thank you very much.